Hi, everyone. It's our pleasure to introduce Cristian Vay from UNC and CONICET, who will tell us about mixed perverse sheaves on flag varieties of Coxeter groups.
Okay, thank you, Nicole, and Karina and Matt for the invitation. It's a pleasure for me to share my work here. I will talk about this joint work with Pramod Ashar and Simon Rich, where we construct a category of perverse sheaf for any Coxeter group. I will start the talk by explaining a little bit about what are the perverse sheaf that we generalized. So let me start for the very beginning. The initial data is a Coxeter system. And for any Coxeter system, we know we have the Coxeter group and also the Hecke algebra. The Coxeter group is defined by generator relation, as all we know. And the most important example for us is that these are the wave groups attached to semi-simple Lie algebra and affine Lie algebra. And also I recall the Hecke algebra in order to put all in context. The Hecke algebra is an algebra over the Laurent polynomials, and we can present it with these generators subject to the relation here that I put here. And also I recall that the Hecke algebra has this standard basis formed by elements labeled by the Coxeter group. And as we know, these elements are defined for by choosing a reduced expression, but really does not care about that. All these elements are equal because of the Braidel relation. And another thing that I want to remark and to recall is the bar involution of the Hecke algebra, but it's an algebra map which sent the B to the inverse and H and the generator HIs to its inverse. Okay, why all these structures are important in representation theory of Lie algebra? Mostly, we can remark this work of Kashtan and Lustig, where they prove this theorem and post these two conjectures and related to the Hecke algebra and Coxeter group, and say how they appear in the representation theory of Lie algebra. So the theorem is a state that there exists this basis which is invariant by the bar involution, and we call now the Kashtan-Lustig basis. For instance, we can say that the element of the basis corresponding to the generators is this one, just an example. And the other thing that say the theorem is how write the Kashtan-Lustig basis in terms of the standard basis. And here is where appear the Kashtan-Lustig polynomials. Okay, and the Kashtan-Lustig conjecture are about this. One of the conjecture is about the Kashtan-Lustig polynomial that they have positive coefficient, and the other conjecture is about the character of the irreducible representation of the Lie algebras. These conjecture now are theorem, and when in the proof of this conjecture is where they appear the perverse sheaf that we are interested on, and the perverse sheaf give the first proof in or RK in the first proof of this conjecture. So I resume here some of the property of the most important property of the perverse sheaf for crystallographic Coxeter groups. That means that there is some Cox-Moody group around. And the most important property of this perverse sheaf, of this category of perverse sheaf, is that it is a highest weight category. And they appear in the representation theory of Lie algebra because they are like a geometric realization of the principal block of the BGG category O. And another thing is that the perverse sheaf gives a categorification of the Hecke algebra. And the geometric means that the geometric nature of the perverse sheaf is that they appear like we can see them like the hertz of a test structure on the bounded derived category of the flag variety of the Cox-Moody group associated. And well, as I said before, they play key roles in the proof of the Kac-Chan-Luchty conjectures. So these are the perverse sheaves that we want to generalize for other Coxeter groups, not only for crystallography. And now I will try to say where we construct the perverse sheaf, which is the ambient category where they appear. So for that, I have to say that after the perverse sheaf, which gives this category, this geometric categorification of the Hecke algebra, several authors try to give an algebraic categorification of the Hecke algebra, and so we can and this we can the first one we can say is this the Sorger model due to Sorger, which give an algebraic categorification, and the other one is the parity complexes due to Juteau, Maudner, and Williamson. And this okay, and then appear the diagrammatic category due to Elias and Williamson. And our work is in the diagrammatic category. What we did was to construct we construct a category of perverse sheaf in this context. Where by perverse sheaf I mean that we will imitate most of the properties that I mentioned in the above slide. And so in this context, and the idea to construct this category of perverse sheaf is to generalize the work of Pramod, Asher, and Simon, who they construct the category of perverse sheaf in this context, in the context of parity sheaf, in parity complexes, because they give they use this for construct certain causality and for study the character of representation of Lie algebras in positive characteristics. So that is more or less the picture of where we are work on and what we do. And now I will try to be a little bit more precise, maybe. And I will start by recalling what are the Elias-Williamson diagrammatic categories. this category was introduced by Ben and Jordi in this paper, and they are construct the initial data for the category is a Coxeter system and a realization of the Coxeter group. As mentioned, these are the realization which mentioned the Ben in the previous talk. Yes, the Elias-Williamson, the Elias-Williamson, the category is presented by generated relation. The objects are labeled by the words on S, and the morphisms are generated by these diagrams, which each diagram represents a morphism between an object in the bottom to a morphism in the top. Yeah, for instance, this is go to BS to be empty, the empty word, or this go from the BS to the BS, the double S, for instance. And this is a tensor category with the tensor product induced by the concatenation of words. The Elias-Williamson diagrammatic category are introduced, I think, almost for any K, but here the K for us is an Ethereum integral domain of finite global dimension, such that finitely generated projective model are free. This assumption is because with this assumption, the category of module over R has a well behavior. Well, for instance, you can take K equal to the integers. Yeah, all these morphisms, as we know, they are satisfy certain relation that I don't mention it. I don't give explicitly, but just I put an example of relation between these morphisms. And this and also I point out that this isomorphism here is like a categorification of the relation of the Hecke algebra for the catalytic basis. No. Just to write. Yeah, this is the okay. And I put here, I recall this definition because will be appear later. D is like a duality in the category, and the category of is a graded category. Okay. Well, one of the important thing of this Elias-Williamson diagrammatic category is that they categorify the Hecke algebra via this isomorphism. Via this assignment, the generator of the category goes to the generator of the Coxeter basis. I point out also that another important thing of the work of Elias-Williamson are the double leaf bases, which also goes to work before it was introduced by Libedinsky. Because they are very important, we explode very explicit these bases are very important for us. Okay. Well, this is the diagrammatic category. Where we construct the perverse sheaf is not in the category or in the diagrammatic category itself. If not, we construct this perverse sheaf in the more general for general Coxeter groups inside this B equivariant category, which was introduced by Pramod, by Asher, Makizumi, Rich, and Williamson in this paper. This is a big derived category. I think this derived is not the one. The big equivalent category is the bounded homotopy category of the Lewis-Williamson diagrammatic category. And our first, or I can say that our first main result, and I will try to explain here, is that we construct a test structure in this triangulated category using the gluing formalism of Beilinson, Bernstein, and Daly. So this is the first result that I will mention in seconds. So I in the next slide, I will try to explain what is this gluing formalism and what is the test structure and how this produce the perverse category. Okay. So if the first ingredient for the gluing formalism is like a sheaf of B equivalent categories. We construct for any. We consider the Coxeter group as with the topology induced by the order, the Brohat order, induced by the Brohat order. So this is then the Coxeter group is a topological space, and then for any closed set and any locally closed set, which is the difference of two closed, we construct we consider these categories. The diagrammatic subcategory generated by the reduced words, the object corresponding to the reduced word. And for the locally closed set, we consider a quotient between the two subcategories associated to the corresponding closed subset. These are subcategory or quotient category of diagrammatic category. And then we consider all the possible homotopy category of this diagrammatic category. This is like a sheaf of B equivalent category for sure. This is one of the ingredients for the gluing formalism. And the other one, okay, before the other one, I will mention an example of these categories. For instance, if you take an element in the group, in the Coxeter group, this set is locally closed because it's the difference between all the elements smaller or equal to W minus all the elements strictly minor than the W. The locally closed set. So when you take the quotient of the diagrammatic category associated to this, and you quotient about the diagrammatic category associated to the other closest subset, what you obtain is this the category of free modules over R. And this isomorphism is a consequence. Is also in the work of Elias and Williamson, and this is a consequence of the double life basis. And when you take the homotopy category of the free modules, you obtain the derived category of all the module because of this is because the hypothesis what we consider we put on K, because of K has a well behavior the homotopy category of the free model is equivalent to the derived category of the models. And here I will use this as example to recall what is a T structure and the heart of the T of a T structure. The T structure in this case, or T structure. The T structure is defined for any no, it's one can construct T structure in the triangulated categories, and this is a data is a pair. The structure is a pair of two triangulated subcategories. Satisfying certain properties. In the case of the derived category of an abelian category, these two, there is a natural T structure, which are in this case all the objects is generated by the object with zero cohomology in negative degree, and the other is defined analogous. This is an example of T structure in the derived category of any abelian category. And the other thing, if a triangulated category has a T structure, then the intersection of the two subcategories give an abelian category. If you take intersection, it is abelian. It is an abelian category because of the properties satisfied by the T structure. One proof that it is an abelian category. And in the case of the derived category of an abelian category, what one obtain here is in this example is the model category of over R. Or if you have, instead of mod, you have any other abelian category, what you obtain is the initial abelian category. So this is to have an idea what is a T structure, what is a heart. And now now I am in the second part of the gluing. I recall the first ingredient for the gluing is all these categories associated to the closed and locally closed subsets. And the other thing that we have to construct in order to have a gluing formalist is these 6 functors between all these categories, and satisfying certain properties. Yeah, for instance, the functor in the top has to be left adjoint of the functor in the middle, and the functor in the bottom had to be right adjoint of the functor in the middle. Okay, we construct all this. It is more one of the more laborious part. And once we have all these functor, we have defined all the functor, we can also define analogous functor, not just for closed and locally closed set, if not for any open set and yes, for any open set. Okay. So with the with this gluing formalism is what it allow us to construct then the T structure with which I explain in a second. But before we can construct the standard and co-standard object using these all functors. In particular, how do we construct these functors? This standard and co-standard object. We have to we take this canonical object in the category in this diagrammatic category, this canonical object is the free module of rank 1. So, and as I mentioned before, the homotopy category, we take this the homotopy category of this diagrammatic category, and we have this factor that we construct in the gluing formalies. We have this y check and y star, and so if we take the canonical element in degree 0 in the homotopy category and push forward using these two maps, these two functors, and then that is we call the standard and co-standard object. For instance, the co-standard object corresponding to neutral element is just the object corresponding to the empty word, and the standard object corresponding to S in the Coxeter system. You obtain these complexes where this is in degree 1 and this is in degree, and this is in degree 0 and this is in degree 1, and this is in degree 0 and this is in degree -1 for in the case of the co-standard object. Okay. Why these objects are important? And now is one of the first results that we can mention is that this standard object can be obtained like a tensor product between the standard objects in the associated to a reduced word, to the reduced expression of W. And the same happens with the co-standard object. This is like in the Hecke algebra. And moreover, that we prove is that this B equivariant category categorifies the Hecke algebra via this assignment. The element corresponding to the empty word go to B, and the standard object has to be go to the standard generator of the Hecke algebra. So this gives a new proof of the categorification due to Elias and Williamson, because the diagrammatic category and its homotopy category have isomorphic rotating groups. Okay. Okay. And also I can say that we made this the advantage to take this homotopy category and then take the T structure and all these gluing formalities allows us to prove this categorification for any for a K, almost for any K, because we extend the result of Elias and Williamson, where they consider K to be a field or a complete local ring. Okay. Well, as I said before, the gluing formalities allow us to define a T structure in the B equivariant category, which consists in put all the T structure what I recall it for in the case of the singleton. The B equivariant category is the derived category of modules. So we have here a T structure, and using T structure we can induce a T structure in all the B equivariant category because of the gluing formats. And if we take the intersection of these two subcategories, we obtain this category of perverse object which is an abelian category. This is not the category of perverse sheaf that we want, because we have to do another thing, because it is not it is an abelian, but it is not a highest weight category, as I will explain later. Okay, so however, we can prove some important properties, that these properties follow mostly from the fact that this category is constructed using the gluing formalism, and we have this T structure and so on. Well, we have this a characterization of the home space between the standard and quasi-standard object, and in the case K is a field, this category is the simple objects are constructed in this way, are the image of the only map between the standard and co-standard model. And another property is that it is a Jordan-Herder category. Well, and as I said before, all the simple models are this.
Christian, I have a question.
Yes.
What is R to the M? Is that a rank M free R module?
R to the M is the homogeneous component of degree 2M, because R is the symmetric of the realization, the polynomial over the realization of the Coxeter group. So it's the homogeneous component of degree 2M.
Thank you.
Yeah. Okay. So and because mostly this is not the highest weight category, because of appear more homes, more morphic between this standard and quasi-standard object. But okay, for this reason we have to take another category, and now I will introduce the perverse sheaf category in the more general setting that we defined. For that, we have to consider the right equivariant category, which also was defined by Asher, Makizumi, Rich, and Williamson. And this is constructed as before, is the homotopy category of a diagrammatic category, but now the home space are formed tensoring on the left by K. So I don't recall if I said before, but the B equivariant category is a tensor category, but the right equivariant category is not a tensor category. Instead, it is a right module category over B. Okay. So we can repeat all, produce the gluing formalism, and define a test structure on this right equivariant category. And the heart of this T structure is what we call the category of perverse sheaf on this Coxeter group. So this is our generalization of perverse sheaf for any Coxeter group. And okay, one of the things is between that we have to prove in order to continue with the is that the forgetful factor between the B equivariant category and the right equivariant category is T exact. So we define using the standard quasi-standard object in the right equivariant category like as the image of the standard quasi-standard object of the B equivariant category. So as the forgetful factor is T exact, these standard quasi-standard objects are perverse, are in the heart of the T structure, are perverse sheaf. And because we are killing all, we are tensoring on the left by K, the home between this standard and co-standard object are 0 except when X and Y are equal and M and N are equal to 0. So this is the K fact in order to prove that this category of perverse sheaf that we call category of perverse sheaf in this general context, it is a graded highest weight category, where the standard object and the co-standard object are this delta nabla, and the simple modules are the image of the only map between these two objects. For that, we have to assume that K is field. And this category of perverse sheaf emulate more of the property of the category of the BG category O in the case of Lie algebras. For instance, we have a characterization of the socle and the head, and also we have this characterization of the home between different standard objects. This is like the BGG resolution. We have only one map between these standard objects if are associated to elements W less or equal than Y, and this only map will be injective in this up to sheaf. No, yeah, it is the sheaf. And the other thing that we can construct in the highest weight category is to consider the tilting object. And I'm following the same idea from Pramod and Simon in this paper. One can prove that the homotopy category of tilting object is equivalent to the derived category of the perverse sheaf, and it is equivalent to the right equivalent category. These are all these properties are certified also in the PG category O. And also for them we have also a Ringel duality between in the perverse sheaf. When the Coxeter group is finite and we have and K is a field. In this case, if we tensoring by the standard object in the B equivalent category corresponding to the longest element, they produce an equivalence of a triangulated category in the right equivalent category. And well, interchange a standard and co-standard object, and interchange tilting object and projective and injective and tilting, and also the tilting object or corresponding to the longest element is projective and injective. So in conclusion, this category of perverse sheaf that we defined for any Coxeter group imitate most of the property or have most of the property that are certified by the perverse sheaf in the case of the crystallographic Coxeter group that I mentioned at the beginning. So I think it is all. Thank you.
All right, excellent. Thank you so much, Cristian. Let's please thank our speaker. Does anyone have any questions?
I have a question.
Yeah.
So the simple objects, they are in general not the indecomposable Struggle-Boy modules or objects.
Sorry?
So the simple objects here in your highest weight category are not, because in characteristic 0, they are the indecomposables.
Yeah.
In characteristic P, they are not?
No, you see you say the simple object?
Yes.
Yeah, these are the simple of this highest weight category. And you say is they are in the composable, is they coincide with the in the composable in the sorted by models?
Yeah, concentrated in degree 0.
No, I don't remember now. And under certain assumption, they are coincide, but we cannot prove all this for all.
But it might be that it's possible that they immune positive characteristic.
It's possible, but we don't have an example where this happens.
Okay.
Any other questions? All right, if there are no more, then let's please thank our speaker again.
Thank you.